and he will speak about presymplectic minimal models of local gauge theories. Maxim, you are welcome. Let's begin.
Okay, thank you very much, and thanks for giving an opportunity to give a talk here. So it's a continuation of an old story. During several years, I had a few talks here devoted to this research program, if you want. And today's talk is like next step, well, maybe step, a little bit side step of this direction. And the main idea is how can we associate to local gauge theories and partial differential equations in particular, certain finite dimensional objects of graded graded geometric nature, which are in a certain sense canonical. So it's slightly different from, although deeply related to geometry of PDE, where typically you want to consider something infinite dimensional, unless the equation in question is not of finite type, but it is deeply related. Of course, there is nothing really deep, because we know that if you're interested in Lagrangian or variational systems, forget about gauge for the moment. The variational PDEs. What does it mean? It means that we have a certain bundle, and then we can see that it's jets. So we have E over X. X is a space of independent variables, so what physicists call space-time in field theory applications. So sections of the bundle the fields in physics terminology. And if we are talking about variational system, we can actually consider, instead of infinite bundle, we can consider finite bundle, a certain K. And then there is a Lagrangian, which is a form of type n0, where n is dimension of X is n of this JK. And this gives us a finite dimensional geometrical object, which is finite jets together with Lagrange function. Of course, we can always uplift it to infinite jet bundle to have everything well defined. And from this L, we can extract other Lagrange equations. So we have Lagrangian, we can write down action. So if sigma is a section X to E, then we say that our action function evaluated on this section is just an integral over X of the Lagrange function, Lagrange form, strictly speaking. So this gives us a standard setup for variational equations, and because we can limit the order of jets to a finite number, because L is a local function, so such case must exist. In principle, we can say that there is a finite dimensional geometric object which knows everything about our variational PDE. But of course, there is a huge ambiguity, and it's highly non-invariant, because I can realize my system in terms of one or another jet space. I can restrict this K to be, if I take K higher than this given K, nothing changes, but still I have a different manifold in the game. So this approach is, of course, known since, I don't know, probably for centuries already. And in my opinion, it's not fully satisfactory, because this restriction to finite dimensional geometry is somewhat artificial and not really invariant. Okay.
Well, in which respect is it not invariant? I'm trying to follow.
Well, because I said variational PDE, I can embed in one or another jet bundle, right? But the fiber can be different.
And whichever you do, K will not change.
No, it will.
It will.
Or it's also quite arbitrary. Of course, you can, given a jet bundle, you can find the minimal possible K. In this sense, it is sort of invariant. But I can easily give you, for a given equation, like a bigger E. That's what people call auxiliary fields. I just add as empty, well, not empty equations, like defining one variable in terms of.
But invariant, you don't mean invariant with respect to change of coordinates or something like this. When you say invariant, you don't.
No, it's more in kind of general sense that it's a construction. It's not in like. You see, like the equation manifold is an invariant object associated to a given PDE, right? Or you can take it as a definition. While jet bundle is just a way to describe it.
Mm-hmm.
Of course, usually we work in terms of jet bundle because it's nearly impossible to work in terms of equation manifold. But still, as a matter of principle, invariant object is equation manifold, not the jet bundle. While Lagrangian formalism is deeply attached to jet bundles. So the general strategy is the idea is to get rid of this restriction, to be able to work with variational systems, not in terms of jet bundle, but in terms of analogs of PDE equation manifolds, and also to be able to get rid of, to avoid this infinite dimensionality of equation manifold. Because, and it turns out that for some gauge systems which are to theoretical interest, let's say there are some very nice graded geometrical objects which to some extent answer this question. So that's the idea.
Okay.
So before going to really PDEs and jet theory, let me give you a kind of toy model for DV or PDE. Not so important in this case. So we are in 0 dimension. So we're not talking about really differential equation. Let's talk about, let's say, algebraic equations, but still at the algebraic level and geometrical level, everything is defined. And it is well known. So what is DV is Maclaurin-Newton's field. It's a way to extend, let's say, Maclaurin-Newton's. It's a way to extend jet bundle description of PDEs to the case of gauge systems in such a way that you have structures which take care of gauge symmetries of your system, of your Lagrange. And if we restrict to a toy model, which is toy model 0 dimensions, 0 dimensional, then what it looks like a manifold M, which is a graded supermanifold in this case. Then we have a homological vector field Q, we have a symplectic structure omega, and we have a degree which traditionally is called Gauss number. That's why I use Gauss instead of DEq to keep DEq for something in addition. And what are conditions? So Q is a vector field. So Q is a vector field on M. It has degree 1. It is homological, so Q squared is 0. Omega has degree, it's not so important now, but let's say it has degree.
This is the same as the Gauss model we're doing.
Oh, yeah.
So Gauss tells you the number of superfields involved.
No, it's just degree, just graded manifold. From a semantical perspective, it's a graded manifold. If we ask for physical interpretation, this plays a crucial role. For the moment, there is a Z-graded. So what we are working with is Z-graded supermanifold. But we can forget about super for simplicity to keep track of only 1 degree. So the greatest super manifold. All our life is there. Okay, so we have a Q structure, so homological vector field. We have symplectic structure for certain reasons. It has degree in the toy model because dimension is 0. In general, it is related to dimension. It should have degree -1. And it should be closed and it should be invariant. So the derivative of omega is 0. So this is toy model of what's from math point of view, it's a toy model of what people call Bartholin-Lukavitsky formalism. If we because omega is Q invariant, there will exist a Hamiltonian. So let's call it LVB. It's just a consequence of this, right? So there is such a function, and degree of this function is 0. And this is called the mass direction. The mass direction. It's like a Lagrangian in 0 dimensions, where x is just a point, but Lagrangian plus extra terms depending on, in general, depending on variables of non-vanishing degree, and these terms are meant to control gauge invariance. So general structure is LBV, is
So
Lagrangian.
does Q represent the gauge symmetry? Is that the point? When you say gauge?
Q represents everything, equations of motion, gauge symmetries.
But I'm just you keep talking about gauge symmetry. Gauge symmetry means the infinitesimal gauge symmetry is Q.
Q plays 2 roles.
No, you said, but it's just that you keep mentioning gauge symmetry.
Yeah, they encoded in Q.
In Q.
Right, but even Q is non-trivial, even for a Laplace equation.
So this group is just one dimension. This group which is that
You engage group.
gauge symmetries is one.
No,
That's
it's
one
not.
general.
It's more general. But this is toy model, so let's don't
In
relate
this
this.
toy model, in this toy model, it's one parameter group.
Not necessarily. It can
Alright.
be multi-dimensional. Depends on your manifold and your Q. But of course, there are no really infinite-dimensional gauge groups because we have finite dimensions. That's true. It's a toy model. But if you think of this, M as a let's say finite dimensional approximation to real space of field histories, then of course everything becomes you can describe field theory. So the structure is like Lagrangian, which depends on variables of degree 0, plus extra terms which take care of gauge invariance. Usually they are written like this. So these are variables of degree 1, variables of degree -1, and these are gauge vector fields. I wrote them in coordinates traditionally. They are vector fields which generate distribution, what's called gauge distribution. So if you move along these vector fields, you will perform gauge transformation. So effectively, you need to take quotient by the distribution generated by these R alphas. But this is really toy model. It's difficult to give a direct physical interpretation to it. It's just an idea. But if there are no variables of a non-zero degree, then it's just a Lagrangian.
So sorry, so in fact, so the answer to my question before is that not all of the gauge actions were mentioned yet, because now you have all of them, right? So these also have the lead derivative of omega is left in there by these vector fields.
Oh yes, of course.
Yes.
Yes. But this L is a Hamiltonian for the field Q. Okay, and from Q squared equals 0 implies that you can write it like this: omega of QQ is 0, which is the same as the Poisson bracket determinant. but in this case, because degree is -1, it is odd bottom bracket, and physics call it anti-bracket, and write it like this, with LDV, LDV is 0. So Moore-Cartan equation, and different, if you want different solutions to this Moore-Cartan equation, correspond to different gauge theories which share the same space M. That's also a possible way to see it. Or you start with a certain gauge theory and then you embed it. You know that it's possible to formulate. Again, it's just a toy model. So what is crucial is that we have this homological vector field, which immediately tells us there is some kind of complex behind, and that's why there are some cohomology, and that's what we expect in gauge theories, because every object of interest is kind of space of equivalence classes, like closed modular insects, some kind of cohomology. But it often happens that it is quite difficult to actually explicitly, well, in this case, maybe it's not so, it's quite difficult to find such an M and Q explicitly, even if you know they exist. So there is a finite generalization, which is the main observation for the thing which I am going to talk about. And this observation is, in fact, not many thing changes if you consider again M, Q, omega, and Gauss, though I should probably stop writing Gauss because everything is Z-graded in this business, so it's automatically assumed, and relax these conditions a little bit. So more specifically, of course, we still insist on Gauss equal to 1, on Gauss omega equal to -1. This is not so interesting part, but, and we also insist that Q preserves omega. So LQ omega is 0, though it's probably also possible to generalize it a little bit, but let's stay with just with this. But then what we give up this very important condition. So now in general, it's not 0 any longer, but we replace it with something which is a generalization still. You see, in symplectic case, Q squared equals 0 is equivalent to this equation, omega Q equal to 0. If,
sorry, but we're still in the symplectic case.
No,
you don't have
no.
omega equals 0 and omega.
No, degree is same,
And
but now I allow omega to be degenerate.
And you still have d omega is 0.
Yes.
You allow omega to be degenerate.
D omega is 0, right? So this stays, but this is replaced with just this equation. Omega QQ is 0. So in principle, we have a non-trivial situation where Q doesn't square to 0, but this equation is satisfied. And as we are going to see that these situations, in fact, are quite useful in applications in field theory for concrete models. So, in which sense this generalized, so this I call, well, this.
Actually, I'm sorry, I'm sorry, but the statement that omega is non-degenerate, because we are in super context.
Yeah.
I mean, normally, because if omega was non-degenerate, then you would have to have omega QQ could not be 0. Right? But in fact, omega QQ is 0 in the non-degenerate case. So what does non-degenerate mean in this super context?
Omega is symplectic.
Yeah.
Omega is symplectic.
But it still has the property that there exists a vector field which is kills it.
If you can substitute it twice. It's an
stupid question.
It's an odd vector field. It's not trivial equation. It's a kind of Moore-Cartan equation.
Sorry.
So this I would call weak presymplectic. It's of course a very bad name. As usually, everything is work in progress in a sense. Oh, by the way, I should have mentioned that it is based on something which I had which I put on archive about a year ago, and which
Maxim, I'm sorry, you mean by presymplectic that it may be degenerate?
Yes,
or
exactly.
something? Just that.
Degenerate. Everything is the same, but I give up invertibility of that.
Yeah, okay, yes, thanks. Yes.
I did omega not. Because I also didn't catch this, and he didn't catch.
Okay.
It. Just right. Omega is not. It's not non-degenerate.
Omega in general. Omega not invertible. In general.
Yeah.
Invertible.
Yeah.
Okay. So it's a slight generalization, but it's going to be, as I said, quite useful, actually. But the thing is that this data again defines locally under regularity assumption the same story. So there is a kind of naive lemma. I'm sure it must be known because it's very simple differential geometry, nothing more than that. But I don't know where it is written. So a lemma is as follows. So if omega, so in this setup, if we are given with this object, if omega is regular, then locally we can take a quotient by the kernel distribution of it. So we can take m over k, and k is kernel of omega in vector fields. So we can take a symplectic quotient, and we know that on symplectic quotient we get a symplectic form already, omega twin, and also q, because it preserves omega, it preserves the distribution. It is well defined on functions which are constant along the leaves of along the distribution. So it's also perfectly defined. So you get a q trivial, and then it simply the same equation stays because it's functorial. So you just get that that omega trivial of q trivial is 0. But now omega trivial is symplectic, and this means that q trivial is just a Hamiltonian vector field with certain Hamiltonian LBV also trivial. I write it like this, so the bracket is something. So one can think of this procedure, one can think of this object as a way to generate, at least in principle, maybe this object is quite complicated and it's difficult to write it explicitly, to work with it. So you prefer to work with this object, which can be simple, but still you are sure that under regularity assumptions, on this quotient, you get just a usual constant rank. So the distribution has constant, the kernel distribution has constant rank. So it's a way to encode these objects, if you want. And it's going to be useful. Of course, it's not enough, because naively, these are toy models, and it's still not sufficiently sophisticated to give something meaningful, because if omega is regular, it means that, well, essentially you just get this in good coordinates. Still it can be useful, but not very useful. What is crucial is that in real applications, one can also relax the regularity conditions. The regularity condition in such a way that nevertheless, after certain, I don't know the name for such a procedure, it contains
It's reduction. It's reduction. It's like a.
No, I will explain. Okay. So in applications, you're also going to meet formally irregular omegas, and these are most interesting guys. That's those which really help somehow to get something very concise associated to systems like Young-Mills, Lagrangian, or things like that, but still they are regular in a certain special sense. So there is a generalization of regularity conditions. So something is still regular, something important is still regular. So there is no cheating, but it's not naively a regularity of these formulas. Okay, good. So much about toy model, and let's slowly get to field theory and to partial differential equations. So what happens? So now I'm going to explain what is BV in field theory. So this was BV in 0 dimensions. I explained. Now I want BV field theory.
Thing is, K is subspace in the tangent. It's
It's a bundle of tangent
Yeah.
bundle.
So the point is that it's not strictly speaking not M mod K, but it's vector M mod.
Oh yeah,
So it's local anyway. It's local anyway. So I can imagine that you go to a point and the rank is constant in the neighborhood of this point.
Yeah,
It doesn't have to be a global thing, just
Yes,
exactly
yes,
local
yes,
thing.
yes,
I can imagine this happens.
Yes. Though I don't have much non-trivial examples,
But that's what,
but
when you say non-constant rank, I guess that's what you're referring to. No? The fact that this is not really M mod K anyway, it's TM. It's it's vector mod.
no, what I mean is, I'm not sure I express myself. So this is M, right? And we have a distribution. So it's integrable because invertible in
K is integrable.
yeah, because only this flows.
Yes.
The kernel distribution is integrable.
Okay.
So you can get you get a foliation by integral submanifolds, and by M over K, I just mean the quotient. Of course, in general, it is defined only locally, and these sort of tricks are always local in my talk. So let's not get into. And sometimes indeed it happens that you need to exclude points where rank jumps, for instance, and where rank is okay, you can do this and this works. Okay, so let's go to because we need this ingredient. What is BV in field theory? Instead of just what in field theory, what we have a fiber bundle of X, which is a bundle of fields. But because we want BV, so we also want to encode gauge symmetries in the game. So E is the fiber is a graded method. So in addition to just dependent variables which are degree 0 coordinates on the fibers of this guy, we have coordinates which are of degree 1, -1, 2, -2, depends on the model. Of course, they should be paired to have symplectic structure. And there is the BV symplectic structure, which is a n+2 form. So omega, which is in n+2 of E. So on a total space, there is an n+2. N is again dimension of space-time. Such a form, which has the following in local. It's possible to say it invariantly, but I prefer to write a formula. Omega has the following structure. It's a volume form if you pick trivialization times some omega AB of psi x to psi a to psi x. Psi's are fiber coordinates. So it's like two form is values in volume. Volume form is value in two form. I don't know which way is better. So of course we need a volume form because we're going to integrate at some stage. So that's what symplectic structure in field theory should look like. And degree of this guy, still we have a Gauss degree. Everything is graded in our life. Z graded. And
these psi's are all variables for some reason, or not necessarily?
Not necessarily. So some of them are just degree 0, bosonic, these are fields, and some of them are Gauss degree 1, anti-commuting. Of course, if it's supersymmetric, then you have two different gradings, but let's don't complicate things. Of course, everything extends to super case, but let's say it's just Z graded. Okay, and of course we require this omega AB, so this is AB, omega is E. That's what means symplectic. Of course, it's not a symplectic form, it's n+2 form on the total space. But let's ask this thing to be invertible. This can be formalized like if it vanishes on a vertical vector, it means that vertical vector is zero. That means invertible. But this matrix is invertible at each point. That's all I want to say this, in terms of components. Okay, then we go to infinite jets of E. And we introduce S, which is called Berzin differential. It's more or less same Q which we had here, but for some reasons I changed notation because Q is going to show up again later. So degree of S.
Could you say what S does? Which is it's
vector field.
Yeah, I see that vector field.
Yeah,
On E.
Yeah, vector on jets. And it is evolutionary and vertical. I don't know, evolutionary doesn't imply vertical. What are standard definitions? Well, let me say both, and then it's going to be evolutionary and vertical. Okay, and this is called Berzin differential. And also we require. Pardon?
I'm sorry. We have in E we have these psi variables, and S is evolutionary in all the variables, including psi. Yes.
Just an evolutionary vector field on this jet bar. Vertical evolutionary vector field of degree 1. So if you want to coordinate, it means that S is something like SA dO d psi A plus d mu SA dO d psi A mu, like first jet coordinates, instead of infinite.
It doesn't do anything to X.
Pardon?
It's vertical means it doesn't have no d by dx.
Yeah, S on X mu is zero.
Yeah, that's the
Vertical. It's tangent. It's tangent to fibers of the jet bundle, and it is evolutionary preserves Cartan distribution. So that's why it has this form. Okay, and also we require it to be Hamiltonian, so to be compatible with the symplectic structure, which means by some abuse of conventions, I pull it back to jet bundle from the initial bundle and do not change convention because it's we don't have too many letters and our memory is limited. So what we require that if we take the degree of this structure omega pulled back to jets, of course now it's pulled back to jets, that's where the real life happens, plus it is equal to the age of something. So it is preserved, so this Berzin differential preserves symplectic structure modular total derivatives, modular DH terms from which it follows that there exists a Hamiltonian. If you
sorry, what's DH? I missed.
horizontal differential on the jet bundle, the canonical horizontal. So on jet bundle we have the RAM which is decomposed into vertical and horizontal pieces because we have fibers and we have Cartan connection, so we have the.
You need a connection.
Pardon?
There is a connection somewhere.
There is a canonical connection on jets, right? The Cartan connection, which is essentially this total derivatives. The horizontal guys, they define horizontal subspace at each space, and then your forms you can decompose them with respect to this B degree, horizontal, vertical, and you around decompose this into the sum, and you get variation of the complex. Then you apply some statements about relation to complex, and you know that from this there exists a Hamiltonian. So it means that if I substitute S into omega, it is dV of something. Now it's really Lagrangian, dV Lagrangian, plus again something dH exact.
Does that correspond to this something to do with modular integration of the data?
Yeah, exactly.
Can you just say some words about that, because I'm a bit lost?
Yeah, if you have, yeah, so this yes, so what is this LDV? This LDV is an element of N0 forms of infinite jets, right? N horizontal, because here we have N, right?
Where is LB? Where is LB?
Here. It's a Hamiltonian.
Yes.
It's a Hamiltonian for S.
Okay. Mhm.
Because omega is a horizontal N form, it contains N dx's. This guy, and this is just a vector field, this guy is again horizontal top form. And it sits here. But it's easy to see that it is defined by this equation up to dH exact something. Because if we add something dH exact, it goes through, it gives like terminal solutions. And this corresponds to boundary terms, because if we now want to write section SVD, which whose value on section is just an integral over x of sigma star of LVD prolongation. If I have a section of T, I prolong it to a section of jet band.
So sigma is a section of E.
Yeah, section of E.
Yeah.
There is a canonical prolongation to a section of a jet bundle, because I need to apply it to a function on jets, not on E. Okay, and if here I add something dH exact, it gives me, through the properties of the sigma star, it gives me D exact on the base. So it's a boundary term. So if, for instance, X is compact, it is 0. Or I need to take care of boundary conditions. And in physics, these are most interesting stories. It's about these boundary terms and asymptotic symmetries and all the business, but that's different. For the moment, we ignore it. We just do formal relational calculus. Okay. Good. So this is classical BE in jet bundle language, well-known stuff. Though it's difficult to find where it is written properly and carefully in such terms, because either it's like physicists write and they are very clumsy about this jet bundle geometry and not very invariant, or most people, they don't like it somehow, they prefer to use different language, but well, it's known, of course it's known, if you compile what is. And this is what I would call BE in local field theory. So that's the way to describe Lagrangian gauge systems. It's like a good way, proper way, because this data knows everything, not only about Lagrangian equation of motion, Lagrangian equation of motion, but also this structure knows everything about gauge transformation, etc. In these terms, we can also define, for instance, what are solutions. If you want, even irrespective of action, just in terms of this bundle and in terms of S, we know what solutions are. So it's like definition. So this geometric data.
I mean, solutions of order Lagrange.
Yes. What are they? They are. They are going to be solutions of Euler Lagrange, but S knows already everything. We don't need Euler Lagrange equation somehow, because they are already encoded in this business. So definition sigma, it's a section sigma x to E is a solution. Because important to what I learned from Alec, Yosif, and literature is that it is very important to distinguish equation and solution. These are two. The equation is kind of geometrical object, and solution is certain object in this. So that's why I want to define solution. So what is solution? It's a section of this galley. If, of course, I need to take prolongation, that's a standard story. I make a canonical section of jet bundle out of this sigma. So I take prolongation, and then I take a condensation with S. Pullback of prolongation, and it should be zero. So in other words, that S vanishes, so that the section seen as a submanifold of the jet bundle belongs to the zero locus of S. This means that sigma is a solution. It's very similar to, if you want to, again, this PD geometry story. And the thing is that equations of motion sit inside S. They are like, they sit in certain components of this vector field. Stuff is organized like this. Even if the system is not gauge, S has the form of Euler-Lagrange equation multiplied by derivative with respect to certain extra variables called antifield in this business, and S actually becomes Presymplectic differential of the surface of the equation manifold seen as a surface in this jet bundle. And this precisely, so zero locus of course located precisely this equation manifold. Section belongs to equation, or prolonged section belongs to equation manifold means it is solution, right? It's a section of equation manifold. Okay, good. So now we know how do we speak about gauge theories in terms of BV, in terms of jet bundles. But as I mentioned, actually we want to avoid usage of jet bundle because we are interested in invariant language. In fact, this BV language is very good, powerful, but if you really look at some applications, you will see that it contains many kind of unnecessary variables. It's very heavy. All these bundles, in addition to fields, you have plenty of extra variables, all these lost fields, antifields, etc. There are too many of them, and you get a feeling that there is something too much and not invariant. So you want to minimize all this. So what is the idea of minimization? First of all, it's very easy to do. This I think I explained a couple of times on similar seminars. Here, you go to the object which is called gauge PD, which is like BD-like extension of PD. So for the moment, what I'm going to do is to forget about symplectic structure, because Lagrangian is a tricky object. So forget about, for the moment, then we get back to it. Forget about symplectic structure, and also because we forget about omega, we also forget about Lagrangian. We don't have it any longer because Lagrangian is just a Hamiltonian of the vector DF. But what we still have, we have a jet bundle of E. We have S, which is evolutionary, which is chronological, and still, as I already mentioned, it knows equations of motion and it knows gauge symmetries. So we know nearly everything about our system, but it's Lagrangian formulation. So it's kind of forgetful functor applied to Lagrangian formalism. You get just PDEs. But okay. So what is the idea to get to this object? Let me quickly remind. Oh, by the way, how am I doing with respect to time? It's already, it's not so bad. 40 minutes, okay. So what am I doing? I want to rephrase, to do a bit more of graded geometry. Because it is instructive and this is the language I'm going to speak. So what I'm doing, because what I'm interested is usually is, for instance, Lagrangian sits there. It's horizontal forms. horizontal forms on J infinity E. Well, all forms, but horizontal in particular. Let's, for the moment, be interested in horizontal forms. There is a graded geometrical way to do it. So what you do, you actually you consider shifted tangent bundle over X. Let's call this projection capital pi, not to confuse it with projection of the initial bundle. So it is known. So what does it mean? It means that we coordinate on the fibers of tangent bundle over X. Their degree is shifted by 1. So they become degree 1 anti-commutative variables. And of course, functions there. So C infinity of T1x is just the rank complex of X. So these are all differential forms of algebra differential forms. And of course, there is a degree, this one, and this degree is a form degree. Okay, so what we are going to do to describe horizontal forms on this guy is a very simple trick. We take pi star of J infinity E. So recall, this guy is a bundle over X, but we have this bundle over X. So we can just pull back this bundle to T1x. And let's call it E. E, and E is the bundle over T1x. Right? Locally, nothing happens. Just the coordinates on the fibers of this T1x, they become like extra coordinates on E. So in coordinates. Now I have x mu, which are my coordinates on X. Now I have theta mu, these are like the x mu, if you want. These are coordinates on fibers of T1x. And I still have coordinates on the fibers, they are unchanged. So all I've done, I've added these thetas. But geometrically, it means that I pull back this jet bundle by this projection. So it's an invariant construction. And now, of course, my functions on this E as an algebra, these are just horizontal forms that we write in this on J infinity of E. So it's a way, just technical way to speak about horizontal forms. You see, the trick of this BV formalism and graded geometry is that we kind of many things which can be said in terms of differential forms. We speak of them as functions somewhere, but on certain graded extension of spaces. And anyway, because we speak graded language, it's kind of a good idea to also describe horizontal forms in the same graded language. I don't insist that it's the only nice way to work. There is nothing deep, it's just a language. You can formulate everything just in terms of usual horizontal forms, but it turns out to be useful, but it's a matter of taste. So I'm not going to defend this point of view that it's the only and the best. But that's the language I speak, so I have to explain. So this is the first observation. Now our so on T1x we have the round differential, which now becomes a vector field one on T1x. And on jet space, we have a horizontal differential, which now becomes such a vector field, theta mu d mu. These are components of total derivative. So it's a horizontal differential. It's just a translation to this language. So we don't have horizontal forms.
Do you use covariant derivative?
d mu is totally, it is covariant derivative, flat covariant derivative with respect to Cartan connection. On jet bundle, it is canonical. On jet bundle, we have these guys. Always. because it's a jet bundle. Interesting. Okay, and let me now rephrase. So what we had? Let me recall. We had this BD formulation. Then we forgot about symplectic structure. So we just stayed with this jet bundle and homological vector field S. So this is, let's say, non-Lagrangian BD, if you want. Okay, then.
So, sorry, this canonical thing, is it just kind of like a prolongation of 3 by dx? Is that what it is?
Yeah, let me write it. D mu is D in coordinates plus psi A mu du psi A plus psi A mu du d psi A mu, etc. So it substitutes the field with its derivative.
Prolongation.
Is it correct to say that it's a horizontal lift, but well, in invariant language you need of course to define this connection invariant.
I'm always confused by the need for this jet bundle, to be honest, because it seems to me that
that's where Lagrangian live.
Yeah, I understand.
And that's where PD is the surface. It's if
it looks to me like it's what it makes sense to say it's a prolongation. When you treat these psi a's as psi a and psi a mu and psi a mu nu and so on as independent variables, then that's
total derivative. These are total derivative.
Yeah.
So then you think it's incorrect to use the word
Strictly speaking, not. I'm afraid not, but Alec knows better because what is. It defines if you have a vector field from vertical, it defines a prolongation. This game defines. It's a structure which defines prolongation, but itself it's a part of data which you haven't just.
Anyway, I see what it is.
Yeah.
And it's invariant. Will it depend on if you change local coordinates? Will it?
Well, if you go not, it's an invariant. The connection is invariant, and you can write it covariant derivative. You can write it in any coordinates. If you choose ugly coordinates, which are not natural, like your independent variables plus derivatives, the transformation always.
This is not prolongation, because if you have prolongation, you can prolong it for first jet, second jet, and so on. But these guys do not exist on any final jets, only on infinite jet, because they take a function from some final jets to jets of high order. So they cannot be restricted.
Yeah, and my message, if you want, of this seminar, well, though it will not be explicit, but the moral is how to avoid this, how to have these structures on some analog of final jets. But to arrive there, we need a fundamental language of infinite jets where everything is nice. Okay. Okay, so we switch the language. So our object is now this E, and let's now define in this grade. Let's again do a definition of solution. Again, it's the same definition, but so sigma. But now sigma, I immediately here sigma was a section of the initial bundle, but now I want to forget about the initial bundle. I want to speak in terms of sections of E. So sigma T1x to E is the solution if, so first of all, one thing is the same in the sigma star composition with S is given, so it belongs to the zero locus of S. It means that vector field S vanish on the image of sigma. And remember, in the definition of solution, we had prolongation. But what does it mean, prolongation? It is also a kind of equation of the same sort. It's a compatibility of section with horizontal, with its covariant constants, if you want, with respect to this connection. In graded geometry language, you can write it as sigma star dh equals to dx sigma star. So dh, look what it looks like. It is dx plus extra terms. So in fact, if you expand it in terms of coordinates, you will see that this is nothing but condition that section sigma is parallel with respect to this Cartan connection, which is exactly the same, that it's a prolongation of the section of the initial bundle. So I just rephrase this definition in fancy language, and I get two conditions. One is that section should belong to zero locus of S. Roughly speaking, this imposes Euler Lagrange equation, if there is a Lagrangian behind, or some equations which are encoded in S. And second, this is very simple, it's just a rephrase, it's just a rephrasing of the fact that sigma is a prolongation of a section of the underlying bundle E, what's the name of font? Calligraphic. Yes.
Sorry.
Yeah.
If sigma lives on zero jets, yes? Between
No, sigma is a section of E.
of E.
E is now jet bundle extended by this theta variable. So roughly, if you want to understand what happens in case of usual PDE, then all fibers do not have non-vanishing degree coordinates. So this section is the same as section X to E, because theta is mapped to nowhere. And this just is a condition that sigma is a prolongation of something. It's a flat section of section. Yep.
What is dx?
Dx is the RAM. Yeah, here it is.
Dx is I
It's
see.
the RAM of the base.
Yes.
Yes, the RAM of the base. So you can say.
But assume that we apply the left hand side of this equation to a function. We get a function finally, yeah?
Yes.
And on the right hand side, we get a form.
No, only functions. Now I don't have forms, only functions.
Because functions means
But
functions
dx composed with sigma star leads us to one forms.
But now horizontal forms are functions for me, because thetas are these thetas are.
You mean in this supersetting? Yes. In the supersetting. Okay.
Yes, I just translated. It's just a translation. Nothing happens.
Correct.
Everything know, but I just write formulas in this graded geometry language. Okay, so we know what how to phrase in this fancy language, how to phrase what we call non-Lagrangian BV.
But what we are doing? So normally a solution is some function which depends on x.
Yes, section is a solution.
Section, but depends on x.
Yes.
And your section depend on x and theta.
Actually, no, because there are. Okay, it's a good question, right? So it's going to be later. For the moment, there is this Gauss degree, and there is form degree, and in fact, I should have mentioned that sigma should preserve both degrees. So theta is sent to nowhere. So I have a degree which is Gauss degree. So the sum of these fiber coordinates psi, they have Gauss degree. But I have also a second degree, which is horizontal form degree, which is now homogeneity in thetas. And indeed, things I forgot to say, I think it would be more careful, though we are going to forget it immediately, to say that sigma is a map. So it's a map that preserves degrees. it's compatible with the degree. That's why theta do not play a role for the moment. They are going to play a role, but not now. For the moment, nothing happens. It's just equivalent to usual language. Nothing else.
Oh, but where this is map. So
yeah, you want
take that.
you want this map because what is sigma star? It's a homomorphism of graded commutative associative algebras of functions. So sigma star is a map from functions on the total space to functions on the base. Both algebras have b degrees. One degree is Gauss number, another degree is homogeneity in theta, horizontal form degree. And this map sigma should respect both. That's why nothing is mapped to thetas, because there is no so sigma star applied to any fiber coordinate produce you a function of x, not on theta. Okay, let me be more explicit. So if I have form degree, let's say fd of theta is 1. All other variables have this degree to be 0. And I have Gauss degree of x is 0, of let me write it later. X of theta is 0. But for some psi,
Psi is 1.
yeah, it's not necessarily. Some of them
may not be 1.
it can be 0, 1, minus 1, whatever.
G Ghost of psi is not 1.
No. It can be, it is quite generic. If we are talking about usual PDE, just
because you said psi can be mixed, it can be
yeah. Fiber is a quite a general graded manifold. And so let's apply sigma star for instance to psi, particular psi naught, which is of degree 0. Of degree 0, and of course it is of form degree 0. Then the result must be some function of x, because it can only be it's a function on the source on T1x of form degree 0 and of Gauss degree 0. But Gauss degree 0, non-trivial Gauss doesn't exist there, so it should be 0 form. It can't be. Well, it can't be a one form, for instance. So again, such a section is parameterized just by some functions of x, and these are field configurations. And where equations of Euler-Lagrange equations sit, they sit in this condition. This condition of prolongation, and this condition tells you that because S knows about equations of motion.
And if you take sigma star of psi with Gauss degree 1, are you going to get something of
0? Necessarily 0.
It will not necessarily 0.
Yes, because on the source space there is nothing of Gauss degree 1. There is only form degree 1. Yeah. So it's very limited. Don't worry, nothing happens here. But now I'm going to change this completely.
But if we apply it to something of form degree 1.
But form degree 1 means that its function just depends, because the only thing from where non-trivial form degree can come is theta.
Yes.
And theta goes to theta. So you multiply theta by some function and it goes to theta multiplied by some function. Nothing. It's consistent. Okay. But what is an important step, which is trivial in the case of PDE, but non-trivial in case of BV, in case of if among psi's are positive degree variables, is the passage to this what I call gauge PDE. Because if you study this object in this language, you quickly realize that you have this description is quite superfluous. You have too many objects. You see, you have 2 degrees. You have form degree and you have Gauss degree. So everything is by grade. Your total space is a jet bundle, which is also quite a serious restriction. And and you have to describe solutions. Same way you can describe distance transformation, but I skip this formula, also as defines gauge transformations of sections, you need two equations. There is a very simple, you can like shrink the description, and it turns out that it is enough and still meaningful. The idea is to take total degree, which is form degree plus God degree, and worry only about it. So you don't see any longer difference between this degree of theta and some degrees of psi. And also to go to, and still, because I'll forget this, I'll still denote it by ghost for some reasons after we do this step. And then we also go to total, we take total differential, which is Q, which is equal to GH plus S. Because this raises horizontal form degree by 1, this raises dot degree by 1, it's homogeneous in total degree. So we just take total complexity by complexity if you want. But of course, in real definition, you forget about this. You can consider more general situation than that. And these two equations imply that actually the definition of solution may look like this. Sigma star Q is equal to dx sigma star. And also that pi star, this is my projection, pi is E T1x. T1x is the pi star dx is equal to Q pi star. This means that is a projection of Q, so Q projects to dx in algebraic language. So what I collected here is the definition of GHPD. But now also I don't require E to be a jet bundle. Still, I have a fiber bundle of graded manifolds. So I have E, Q, T1x, and Gauss number. And this allows me satisfying condition that Q squares to 0, that Q projects to dx, and some technical assumptions which I'm not going to discuss now. And this data is enough to define a gauge system. Why? Because I can say, okay, guys satisfying these are solutions, and these are non-trivial differential equations, because inside here there is a d over dx, so it's first order, it's a system of first order differential equations. Plus I can write down gauge transformations. I can say that if sigma is a solution, then variation of a solution, the gauge variation, if epsilon is a parameter of gauge transformation, I'll define what it is. It looks like this. It is dx epsilon star plus epsilon star q. And what is epsilon? Epsilon is a map from C infinity E to C infinity T1x of degree 1. Goes with epsilon is also minus 1. And it's okay. So if I have such a guy, it's like it's a map of degree -1. Then I can form such an object, and it preserves the. So if I shift sigma by such a variation, then sigma, if sigma was a solution, it remains to be a solution. So, and the same way I can define what's called gauge for gauge symmetries. But let's not get into this sophisticated stuff. So it turns out that this simple geometrical option or object, sometimes people call it Q-bundle, because it's just a bundle in the category of differential graded manifolds, right? So the total space is a differential graded manifold, the Q manifold is the same. The base space is also Q manifold, so a specific Q manifold T1x, and projection respects the digit structure. So it preserves the degree and it preserves the homological vector fields. And it turns out that locally, I don't know the global statement, and this is not quite a trivial statement, and I only know the technically involved proof in terms of local coordinates, that in fact, if I build this gauge PD out of DB system, so which means that I took Q to be DH plus S, degree to be total degree, and do everything properly, then it describes the same gauge system. So it means what I prove that by this gauge PD, I can describe everything, at least locally, which I can describe using usual BB formalism. So in particular, I describe all possible local gauge theorems, reasonable ones. So it's not a very simple step, but it's conceptually very important because this object is much better. We have much less structures. We just have a bundle in fiber bundle in DG category, and it gives us it's a way to describe sophisticated system of partial differential equations, which are invariant under gauge symmetries, again encoded in this Q. So a simple example is just PD. Usual PD corresponds to the situation if dot degree of all fiber coordinates is 0. Then nothing interesting happens, and this condition just tells us that this Q, in this case Q, should look like this because of degree reasoning. It is dx plus some gamma of psi x mu derivative psi a. So it's like a covariance derivative, and if you can see the equations, you will see a generic system of first order equations. So usual theory of PDE you can embed into this language in a trivial way, but something non-trivial happens if you have variables of non-vanishing degree. Another maybe typical example, which
in this trivial example, what is E?
E is just your equation manifold as a bundle of space-time pulled back to T1x. So you start with E prime over x. This is your equation manifold, equipped with Cartan distribution. So then you take horizontal forms on it. Then you have DH, horizontal differential, which is important. Then you switch to super language and you write it as Q. It's just different way of parameterizing same object, which you nothing. In this case, nothing happens. It's just a strange way. Maybe it's quite unnatural for people who are used to the standard geometry. But it's useful if you go for this gauge objects.
But would it be possible if you would like to take for E take the jets and include to S Kashul-Tate?
Exactly. Yeah, it's BB. Yeah, that's what we started with. If you want, yeah, that's another good example where you take jet bundle, you build Presymplectic, you take S to be Presymplectic, and you take Q to be DH plus S. This is equivalent description of the same PDE, but in this language you can even think of their relation. Suppose I want to describe PD in two different languages, jet language, then I take this cube, and in intrinsic terms, when I think of it as an equation manifold, it's such cube, it's different cube. Then one is a kind of equivalent reduction of cube manifolds of another. And it amounts to elimination of some jet coordinates together with these anti-fields, etc. Okay, and maybe one example which is characteristic for gauge story, though it's also kind of naive and known, zero curvature equation as a gauge story. So take E to be E1x, some space-time, x, this is capital X, times a Lie algebra with a degree shifted by 1. And take Q to be X plus Chevalier-Lambert differential here. So if it's a Lie algebra, then G shifted by 1 function there can be thought of as the Chevalier-Lambert complex of this algebra. So if you pick coordinates, this Q CE will be written as C alpha CB where C are coordinates on the Lie algebra with shifted degree, and these are structure constants of the Lie algebra. Or alternatively, I mean, I can write it completely up here, something like half CC in this form is more. But C is the algebra values. Okay, then you can consider what are solutions of this gauge PD, and let's have a look what they are. So first of all, what are sections? So section, of course, I work in terms of pullback. So sigma star of C alpha must be, C alpha has degree 1 because we shifted degree by 1. So C star of C alpha, sigma star of C alpha should be a 1 form, right? It should be an element of degree 1 in the source. So it should look like theta nu A mu of x, for some functions A mu of x, right? Just a generic 1 form. And the equation, this condition, in this case, amount to nothing but dA, if I think of A as a 1 form. Zero curvature equation. This equation is a function of this gauge PD, and you can also write gauge transformation and for it in the same Q, and they look like d of epsilon plus A epsilon. Of course, all my coefficients are probably wrong.
So if this is what you get if you apply
Yeah.
wait a minute, to NEC. Is that what you're saying?
Yeah.
Apply the bottom thing to NEC, and NEC will be written like this, and then you okay.
Yes. Any coordinate. Yes, all of them like algebra. So that's an example of a gauge PD, which is like completely opposite to usual PD. It's if you want, it's like finite type.
Where does the second formula come from? Delta A.
It's from gauge transformation. It's this formula. You see, there is the RAM and there is Q. Q gives you commutator, and the RAM gives you this, and epsilon is the gauge parameter. Of course, it's a topological model, and this description is all known for centuries, but it's another extreme example of gauge PD, and in the between PD and this topological thing, you can find all variety of systems. Okay, but my promise was to say about presymplectic, something presymplectic. So before going to this, just one comment. I don't have time, and I think I talked about these stories, that for gauge PDEs, we have a notion of equivalent reduction. Equivalent reduction. What does it mean? Roughly speaking, locally, I don't have time, and I don't want to get to this long story. Locally, if I have WA, VA, some fiber coordinates, such that QWA is 3A, and they are independent, so it's part of coordinate system, then I can actually go to some globally. Globally, one has to admit to extra constructions. Then I go to a sub-bundle, just like this. It's like elimination of contractible pairs for differential. Locally, this doesn't change. Locally, in geometrical sense, this doesn't change cohomology. Globally, you should say more bonds, but it's also possible. And this gives you a huge flexibility, because actually you can start with one HPD and then you can reduce it by such a procedure. You can eliminate trivial variables, homologically trivial variables, to reduce it. And at the end of the day, you can reduce to something what's called minimal model. If your system is understood like perturbative, like linear plus more, which is the usual linear terms, which is the usual setup in physics where people study perturbatively, then there is even this minimal model theorem from theory of real infinity algebras that locally this minimal model exists and is unique. So it means that to such an object, at least locally, you can find, under some technical assumptions, you can find something which is minimal model, which is unique, and in this sense, it is a kind of invariant object associated to your HPD. And in fact, this minimal model, this E, this zero curvature, which I showed you here, it's a minimal model of, for instance, Chern-Simons theory, if you forget about Lagrangian. Good. As I said, I don't have much time to talk about this, but what I can now discuss, and what is the real reason of this talk, is how can I describe in this language, how can I describe a Lagrangian system? And the message is you need presymplectic structure to be defined on this object, on this BHPD. So let me call it presymplectic BHPDs. Which means that on top of BHPD, I have omega. D omega is 0. Degree of this presymplectic structure should be compatible with dimension. Should be n-1, where n is a space-time dimension. And it should preserve should be compatible with Q. So this is not 0. This is in, I need to explain this. So if we have a bundle, we can define vertical forms there. Even if you don't have connection. We can say that we can take a quotient of if E over, let's say, Y, just G over Y, generic bundle, fiber bundle. Then we can consider all forms from G quotiented by the ideal I, where I is generated by wedge of wedge of right. So I take forms of positive degree on the base. I pull them back to the total space, and I generate the ideal. So naively, these are just forms which contain dy's, right? Where if y small y coordinates here, then in standard coordinate system, where fiber and base coordinates, forms which contain dya proportional to dya are going to be in the ideal. If we take a quotient by them, it's a well-defined procedure. We get algebra of vertical forms, on which there are differential defined, etc. And in fact, also in this setup, if we now take gauge, because GHPD is a bundle, we can consider vertical forms there. So what I ask, although I require omega to be just a concrete representative, it can be generalized, but let's say omega is just a two form now. Now, because I don't have horizontal, omega is two forms. E, which is closed of degree n minus 1, and it is preserved by Q modulo this idea of forms.
Happened to be n form before it was n plus 2, wasn't it? Your n. Omega was n plus 2.
No, it was n at some stage. Yeah. You're right.
Oh, why have you lost n here? I mean, I thought that was the reason for ghost omega is n is not minus 1 but n minus 1. I assume this was related to this n.
It is related.
But why has it gone there?
Because omega is a two form.
This 2 form before was an n plus 2 form.
You see, there is, it's a bit, everything is balanced.
Yeah.
You are asking the right question, but you see, you should think of this omega as a it's a like two, it's a vertical form, it's a vertical two form, and horizontal n form, but of course degree minus 1. But because now we have a total gradient, this minus 1, which do you remember in toy model we have this minus 1, it subtracts this extra 1. Anyway, this is a definition. So this presymplectic GHPD is the GHPD equipped with omega satisfying this. It turns out that this data is enough to how am I doing with respect to time? I think it's already quite. I think I should stop soon. I'm sorry. It's important. Okay. Yes. Okay. This data is enough actually to reconstruct BV. And what is important is that now we are not any longer on jet bundles. They are generic bundles, and still you get a Lagrangian formalism out of it. And the thing is, what you do, you actually consider on which what plays a role of your fields are sections of this bundle E. So our GHPD is a bundle E over T1x. Now, if we have a section sigma T1x, T over T1x, it's T1x. Now, if we have a section sigma T1x to E, right, we can associate an action which is which looks like this. It's an integral over T1x of so what is chi? Chi is a potential for omega. So because omega is closed, and if we are in high dimension, there is no cohomology, so omega is d chi. But there is a one form of chi, such that omega is exact. So you take this one form, you pull it back by your section, and you evaluate it on a vector field, which is the Ram differential. So this gives you kinetic term, and L is a Hamiltonian of omega, because of Q, yeah, because omega is Q invariant, then Q, you know that I'm Q omega is d of certain L plus Forstmann terms in ideal. Yeah, it's a bit of technical nature, but it is important. So this defines your Hamiltonian, and this is precisely the potential in the dimension. But then you can ask me, okay, fine. this is action, but where is, first of all, this section is parameterized by infinite amount of components, because usually this bundle E is infinite dimensions. So section is parameterized by infinite amount of functions, right? And how to interpret it? And the interpretation is that you need to take a symplectic quotient. You need to, so this omega is presymplectic. In general, it's not even regular. But what are these sections? These are, let's say, maps from T1x to the final. So what we are interested in is, and more precisely, supermaps. That's what we need now. Supermaps T1x to the final, local. And the dependence on x is completely passive now for me. So I can even pick a point here. I can put here point P and forget about x dependence. But this is finite dimensional space. It's just Grassmann algebra as the exterior algebra of a tangent space. So what I'm interested in is the space of supermaps from such a graded space to the final. And on this space, I have omega. Right? Again, I can fix to simplify life, not to really speak about infinite dimensional objects, I can fix a point in my x space, because nothing really depends.
Sorry, that's an E there, or an
F.
What is F? Sorry.
Fiber. Because I talk not about sections, about maps now. So what this space of maps look like? So if system are coordinates in here, I ignore x coordinates, they are passive in these considerations. And psi A are coordinates on F, my fields, if you want, then what supermap look like? It look like this. Sigma hat I put hat for supermap of psi A is sine A plus sigma mu psi 1 A mu plus sigma mu psi 2 mu, etc. And of course, this coordinate, because it's a supermap, they get degree, right? So this guy has same degree as psi. This guy has degree because there is theta here. So the degree of this guy is degree of psi minus 1, etc. It's like a superfield. We just describe maps from this superspace to this superspace. And we know that if we have a symplectic structure, we have a presymplectic or symplectic, doesn't matter, structure of this guy, it induces, it's classical geometry, right? If we have a symplectic structure in a bundle, you get, and if you know how to integrate, you get a symplectic structure in space of sections, in the infinite dimensional manifold. The difference here, the space of supermaps, if we forget about x dependence, just finite dimensional. It's finite dimensional manifold again. So it's not, we don't need any functional analysis. And we can induce symplectic structure on this space of supermaps. What it looks like in terms of coordinates, it looks like this. Omega bar is equal to integral d on theta, omega AB sum of theta. Well, x is a parameter, I don't write it. D psi A theta, d psi B theta. Right? Where I just think of this, so psi of theta is this guy, psi of theta is this guy. So I simply I simply think of theta as bookkeeping device to pack coordinates on the space of supermaps to functions in theta, right? And same is differentials, right? And so I take this integral and I get a symplectic structure of the space with coordinates like psi 0, psi 1, psi 2, etc. This is the standard, it's just a graded version of the standard story how symplectic structure on a fiber bundle induces symplectic structure on space of maps. But I just simplified it and want to do it per point to avoid speaking about infinite dimensional spaces. So it's still finite dimensional, and because there is an integration over theta and dimensional integration of theta, and theta carries degree 1, then degree of my omega bar is going to be -1, because it was n minus
So
1.
this integral over theta in the Algorithm integrals.
Yes.
So this omega, it has to depend on these psi's and thetas in such a way that you get a homogeneous
Exactly.
degree, right?
It just picks the top form.
Yeah,
Exactly.
understand.
That's what it does. But because the integration throws away n thetas, the degree from n minus 1 becomes n minus 1, precisely like it should be in B. Okay, and what I need from assumption, I need to assume assumption is that omega bar is regular. And it's much better than to require omega to be regular. I'll show you an example. And this I have to stop with this example.
What is this because omega bar is only defined at a point? Is that the thing?
No, X is positive. It's because omega is usually containing higher power of thetas. And in this sense, seen as a function of theta, it is highly irregular.
But they are integrated away. They're thrown out by the integral.
Yeah, but after they integrated away, you exactly
What do you mean by regular?
usual.
Non-degenerate?
Okay, let me give you an example, and it will. I think it's much better than my
You said it
poor
before.
attempt.
You said before it's constant rank.
Yeah, this omega bar is going to be constant rank.
That's what regular means.
Constant rank, yes. Yosef?
Yeah. What do you mean by regular? Non-degenerate?
Constant rank. No.
Constant rank. Okay.
Yes. Okay, so let me give you an example, which I think clarifies a little bit. So let's do no, before example. Now the main point. After we understood all this, and we know that it is possible to actually, I don't have time to explain this, that actually we can cover all reasonable H series. We can find such presymplectic structure which produce B, etc. And it turns out that this symplectic structure has just differential geometrical two forms on this total space E. They have, although they are strictly speaking not regular, but they are local in the sense that they involve only finite amount of coordinates. So behind there is some kind of finite dimensional geometry, and this finite dimensional geometry you can get to it by considering this omega bar, and if it happens to be regular, you can take a quotient with respect to the kernel distribution, just like in the very first lemma I discussed in this seminar. And this leaves you with something finite dimensional, and that's, in my opinion, the most interesting part. And but once you understand all this, you do a crucial observation that actually all steps to prove that this is a good PV action, etc., go through if you replace condition q squared equal to 0 with weaker condition, which is omega of QQ equal to 0. And this turns out to be crucial.
It's not equal, it's replaced by.
Yeah, yes, so Q is not necessarily. So now I can work with Q, which doesn't square to 0, but satisfies this equation. And still, I can trace in this construction that after I perform symplectic washing to omega bar, just with the same reasoning like I had in the beginning, with this simple lemma, that effectively on a certain subbundle of my jets of E, I get genuine nilpotent Q. So I get back to BV formulation. But once I have this instead of this, in fact, I can immediately start working with finite dimensional E's. I don't need, because infinite, it's
You
like
truncate things.
yes, it's like a clever way to truncate PDE if you want, because what happens is that Q, in case of PDE, Q is just horizontal differential. It's just this total derivative, and it's only nilpotent on infinite jet bundle. But now we are talking about Lagrangian system, but I'm sure it can be done for generic PDEs. But now this equation allows us to work with Q's which are not nilpotent any longer. So we can consistently truncate our jet bundle or our PDE to something finite dimension. And that's exactly what happens in the examples. And now me give you, now I'm ready to give an example which I think is more instructive than these general considerations, which require, of course, more time and power to deal with everything. So the example is the ambits. So what is now my E? I have base space, so I have space-time coordinates, I have theta's, I have ghosts, so this is degree 0, this is degree 1, this is degree 1, and I have FAB, which is kind of curvature, if you want, which is of degree 0. And in fact, I can truncate with this, so it's a finite dimensional graded manifold. And now I have, I can define Q. So Q in the sector of X and theta is just Dirac differential. But here something interesting, it's like a BLST description of Young-Mills. QC is just PC. So C and F are the algebra values. C plus theta F. A B. And QFAB, C and A. Commutator is a Lie algebra commutator. You can think of C and F as matrix values, for instance, in fundamental.
So C represents the connection.
At the end of the day, yes. But for the moment, it's just degree 1 coordinate. So it's a finite dimensional object. This is base, this is fiber, and I work locally. If I really wanted gauge PD description, I should have added infinite amount of higher tensors which encode covariant derivatives of the curvature, which can be non-trivial.
Which I like this what I was calling prolongation, but you.
Yeah, exactly. But now,
okay.
because we can get rid of this, we can easily truncate it to something very small.
So you don't have omega.
But
there's no omega.
It's coming, yeah. So this is my bundle. Now Q square.
What's Q square?
Q square is in general not 0.
In this example?
Yeah, in this example.
Okay.
Because if the algebra is non-abelian, it is in general not 0. If it is abelian, it is 0.
Well, you don't tell us what's Q of theta then.
C0, because it's important. It's not important. So this is I should write. Yeah. Q of theta mu is 0. Right. Okay, and now I can give you symplectic structure. And symplectic structure is omega equal to, let me stay in 4 dimensions for simplicity. So this is total antisymmetric, Lorentz invariant total antisymmetric tensor. Theta A, theta B, and trace here because these are all matrices. Yeah, this is symplectic structure. So this is matrix value, this is matrix value. So we take trace, of course, trace only goes to here. And that's what omega looks like. So you see, it's not symplectic and it's not even regular.
Why is it closed? Okay, okay.
That's a nice way to write it.
Yeah, sure.
Yes. So it's like PDQ if you want.
Sure,
But
yes.
it's covariant, whatever, graded, everything. It's high generalization of Hamiltonian structures. Okay, so this is of course by construction it is closed. As you can see, it only involves variables which are here. I could have added higher tensors, prolongations of this F,
Yeah.
but it's absolutely useless because this symplectic structure has them in the kernel. So anyway, they disappear. This action is not going to depend on them.
And it's blind to the base, by the way. It doesn't care about x's.
Well, it's, if it was not Minkowski space, but curved space, it would depend on x. But here it depends on theta, it's also base. And this is crucial because you see it's not even regular, it is proportional to theta. And theta equals 0,
Yeah.
it vanishes. So it doesn't have a constant rank, it's organized in a tricky way. So it's easy to check that if you do computations of this action, you simply get S of sigma C, sigma F to be just Cauchy solution D for X.
Sorry, who's the psi in this example? Psi is C.
Psi is C and F.
Yeah.
Yes.
So
So
there
D for
are
X,
even variables.
FAB, DAB, whatever is A plus later, B plus something like this. FAB. It's a standard action of Yang-Mills written in first order form. So if you compute it, you get this action. But now you can ask, what about BV? What about symplectic structure and proceed? And this is probably the nicest part. So let's compute omega bar. So what is space of supermaps? So we have two fiber coordinates, C and F. So let's write sigma F of C is C naught plus theta mu A mu plus theta mu C2 mu plus chi, which we don't need, and then sigma F of FAB equal to F0, 0 component, AB. Oh, not mu. Let me also use A.
You can really answer. What is A here?
Capital
A.
it's just notation. It's going to be gauge field. It's it's component sigma star of C. Yeah.
So A is sigma star of C.
Yeah, that's exactly what you see. If I apply super map to C, I get in degree 1 component this stuff. If it is just a usual map, not a super map, then only this we have. Because this doesn't preserve degree, because this gets degree. This is not allowed. Space of.
I'm just wondering why A didn't appear in the action. That's all.
It's sigma star of C. Yeah. But sigma hat super map, I like activate all components, not only components of degree 0. Like all of them. And here the super map of FAB, if F is F0, plus theta C F1 AB C plus theta C theta D F.
But sigma star of F is just F. Sigma star of C is A, but sigma star of F is F.
No, it's just matter of
In the-
zero on top.
action.
In the action, yes. Sorry.
So for some reason, so they are different, in fact. Okay.
Sorry.
Maxim, I just want to take a photograph because I haven't got any papers, so I want to give this as an exercise for myself.
Yeah, sorry, I'm becoming a little bit clumsy. So, okay, so these are coordinates on the fiber, and these are with this component. Either I denote them by different letters or by letters with numbers on top, which is like form degree. So this is 0 form, this is like 1 form because 1 theta, this is 2 form. And now let's compute omega. It's very simple because what we need to do, we need to compute this omega bar, which is integral b and theta of this omega b, d psi a, d psi b, d psi a.
So presumably the fact that omega of q is 0 is a sort of like tricky, is a long exercise, right?
It is an exercise, not completely trivial, but
I might try.
yeah. Okay, so let's compute this guy. As you correctly mentioned, the non-trivial contributions would come when you will have thetas coming from here, here, and here, adding up to top form because it's Bayesian integration. So look at omega. In omega, we already have 2 thetas. So we need to get 2 thetas from these components. So what can be a contribution? First contribution, for instance, the one which contains C naught. C naught can only couple, give something non-trivial, with something quadratic in thetas, because 2 thetas are here. So you need to extract 2 thetas from F, right? So something from 2 thetas here, 2 thetas here, and 0 thetas here. That's the first term. So omega bar is what? Is, of course, all coefficients are dc naught. They will put wedge here for a change. D, but look, here I have 4 indices, A, B, C, D, and 4 thetas. If I do all the integration, I get a total trace. So what is going to be here is AB, where repetition of index means taking a trace.
You told me that you have to take a trace.
Yeah, because if you remember what epsilon symbol is, for thetas you get the connected symbols. It's just simple linear algebra. Okay, so this is the first term. Then the second term is with A, right? So there is 1 theta here, 2 thetas here. So there should be 1 theta coming from F. So it should be F1. So what I'm going to get is DAA, DFA, B1. And here, and then there is a third and last term, which contains this stuff, right? So here already we have 2 thetas here. So it's already 4. So only a 0 can contribute. So we get here DC2 AB.
I'm sorry, what is N here?
What?
N is everything. N is anything.
4. N equals 4.
Yeah, that's true.
I can do it in all dimensions, but
Yes,
simplicity, of course, for dimension, because
Yeah.
physics tells us that it's the nicest one. So it's essentially canonical symplectic structure, and you see, and a constant. So it's perfectly regular, in contrast to this. So this guy is of degree 1. This is of degree -2, right? As it should be, because the symplectic structure should have both degree -1. This is of degree 0. This is because this is Yang-Mills field at the end of the day in the action, right? It's a Yang-Mills field, and this is anti-field, canonically conjugated to it. And this is also of degree 0, curvature, and it's anti-field, which is of degree -1. All the rest, also some components of these guys, they are in the kernel. So we see only total trace of this guy and first trace of this guy enter. All the rest is in the kernel distribution, and you take a quotient and you are staying with this is symplectic space. And this is a correct BV description of this thing. And I forgot to tell you that this thing is of course minimum because it comes from a minimal model of GHPDE for young mills. So it's kind of canonical. People know these formulas, prolonged versions of them for many years. They found them in 80s when trying to compute homology for young mill theory. And they know it's useful because it's a minimal model. There is nothing to eliminate any longer. And this symplectic structure lives on this minimal model. In this sense, it is also minimal. So I don't have a mathematically well-defined notion and proof, but at least this thing in some certain sense, in a perfectly well-defined sense, is a minimal. It's a part of minimal model. It's a truncation of a minimal model in precise mathematical sense, and this symplectic structure is there. And moreover, it kind of defines it because you drop from the full BHPD description of young mills, you drop everything which is in the kernel of this omega, and only stay with something which you can't directly get rid of before passing to this space of supermass. And this small structure, so this graded manifold plus this symplectic structure, knows everything about Batalin-Minkowski formulation of the system. So you reconstruct a proper jet bundle out of kind of nothing. A proper jet bundle where it is embedded as a local BV system. And this jet bundle comes as a quotient of a super jet bundle of this E. So you take this bundle E, you take its associated super jet bundle, on which you have a component of induced symplectic structure is going to be this one, and then you quotient by the kernel, and you get precisely the jet bundle B. So somehow the structure knows in which jet bundle you can embed your system in a standard canonical way. And you can do exactly the same for many examples of, mostly for me, I'm interested in field theories which are interested in QFT, in fundamental interaction. So it's also a very nice story about gravity in this formalism, about chiral young mills and many other models. So one can even consider it as a way of to generate non-topological model, to generate local gauge theories from finite dimensional supergeometry. And at the same time, it can be thought of as a kind of generalization of what is known under the name of AKZ, Alexandrov-Kontsevich-Schwartz, the Baranski procedure, because they were considering symplectic, finite dimensional symplectic version of this story long ago. And they showed that it actually leads to the nice BV descriptions of topological models. And what was not clear is how this procedure can be extended to cover non-topological models, again, mills, for instance. And the message is actually, if you want to stay with something nice and finite dimensional, you need to do two steps. First step, you need to admit omega, which is degenerate. But this is somehow not always enough. But the most important probably step is to give up nilpotency in favor of this tricky omega QQ, this like generalized modern Cartan equation, presymplectic equation. So I think I exhausted my time. So thank you very much for listening.
Thank you very much too. It was very interesting. Well, we had a lot of questions from Ian, but nevertheless, any questions or remarks?
It feels very like there's only two people here, so it feels like a private talk.
Yeah, thank you. I would like to ask a question. May I?
Yes, Kostya, of course.
Yes, Maxim, hello, it's Kostya Drushkov. I would like to ask you the following question. Does this minimal model somehow encode all higher order conservation laws and all other higher order structures?
Directly, not, I think, because it's really a truncation of, if you apply it, like also in your construction, if you apply it to PDEs, then you end up with somehow it's almost like truncated infinite jet space or truncated equation manifold, and of course it's not enough to capture all higher symmetries and higher conservation laws, etc. But at the same time, it produces you a jet bundle, genuine jet bundle, infinite if you want, where you get all the structures and where you can study it. But of course, it is difficult, probably. I don't know the answer, of course, the real answer. But I think it is difficult to make a statement, or nearly impossible, that like higher symmetries are going to be cohomology of this Q in a certain sense. You need to prolong this Q to a superjet bundle, take its equivalence class, and you will finally end up with a genuine description of this PDE, but these are few steps procedure. Yeah. Yes. And of course, yeah, I should have mentioned also that in the case of PDEs, these symplectic structures people study. Of course, you studied these symplectic structures from the usual viewpoint of geometry of PDE. But this is, of course, mostly graded version, which I was interested today. PDE version, yes.
Okay, more questions? Well, Maxim, thanks a lot. We shall continue.
Thank you.
Hopefully, yes, and we agreed to meet next Wednesday. So
yes.
We'll see each other. Thanks a lot. Goodbye.
Maybe one comment, if I wanted to make.
Yeah, sure.
Just to one comment is that I think that this construction is not really related to Lagrange. You
to
can
what?
do to Lagrange because this minimal thing, finite dimensional, I showed how to build it for Lagrangian systems where symplectics are present, and it looks like it works for generic PDEs, but you need different structures to take to get this finite dimensional truncation. But this is
so it will not involve symplectic. You won't have a symplectic form in that case.
Yeah, there will be something different.
Some other device.
But because you see, realistically, what you need is this distribution, this kernel distribution, no matter where it comes from. It should be Q invariant, and that's enough.
Right.
It's like a clever way to truncate PDE to something finite dimensional, but it's not done. It's just a teaser. If you want. Yeah. Yeah. Thank you. Sorry.
Okay, thanks a lot. So we meet in a week. Goodbye.
Yeah, very good. See you.